Welcome back to class, everyone. In today's explainer, we're going to dive deep into the absolutely mind-blowing physics of how thousands of incredibly heavy metal objects manage to stay completely suspended right above our heads. I mean, we rely on satellites every single day, right? But most of us never really stop to think about the incredible orbital mechanics that make our modern hyper-connected life even possible. So let's figure it out. Here's a quick look at our lesson plan for today. We're going to hit 1, the invisible string, 2, Newton's brilliant cannonball, 3, the geostationary magic trick, 4, different orbits for different jobs, 5, the cheat codes of physics, and we'll wrap it all up with 6, satellites in everyday life. All right, let's jump right into section 1, the invisible string, or simply why things don't fall. Let's start with a really relatable everyday action. You pull out your phone, you check your GPS, or maybe you turn on a live sports game. I want you to just pause for a second and think about it. Why doesn't gravity just pull all these multi-million-dollar machines crashing straight down onto us? I mean, we're basically taught from day one that what goes up must come down, right? So what gives? Well, the secret lies in a concept called an orbit. To picture this, I want you to imagine swinging a ball tied to a piece of string. That string is constantly pulling the ball inward towards your hand, while the ball's actual forward speed keeps it circling around you. For a satellite up in space, Earth's gravity acts exactly like that invisible string. It's continuously pulling the satellite inward, but the satellite's forward speed is just so incredibly fast that it keeps circling the planet instead of crashing back down. And this brilliantly illustrates the delicate balance we're talking about here. On one side of the equation, you have inertia. According to Newton's first law, a satellite naturally just wants to travel straight ahead, zooming off into the abyss of space. But on the other side, you have gravity, continuously tugging it inward. These two forces perfectly, flawlessly balance each other out to create a circular motion. By the way, the idea that there is zero gravity in space, that is a huge misconception. Earth's gravity is literally the exact force keeping them up there. Moving on to section 2, Newton's brilliant cannonball. Let's look at the history of falling. To truly grasp how we figured all of this out, we've got to travel way back in time to Sir Isaac Newton. He totally revolutionized physics when he introduced the law of universal gravitation, and he came up with this brilliantly famous thought experiment. He imagined firing a cannonball from the top of a ridiculously high mountain. If you fire it slowly, it obviously falls back to Earth. Fire it a bit faster, it travels farther before it hits the ground. But if you fire it fast enough, as it falls, the Earth's surface actually curves away beneath it at the exact same rate, meaning the satellite is actually in a constant state of freefall, but it's perpetually missing the ground. Now, Newton's theory became reality incredibly fast once the 20th century rolled around. Just look at this timeline. In 1945, the science fiction writer Arthur C. Clarke proposed placing communication satellites in a super high orbit where they'd remain perfectly fixed in the sky. At the time, that sounded like pure sci-fi. But fast forward to October 1957, and the Soviet Union actually launched Sputnik 1, a little sphere weighing just 83.6 kilograms. And literally months later, in 1958, the US launched Explorer 1, which discovered the Van Allen radiation belts. Boom, the space age was officially born. So, how do we actually do it today? Getting these complex machines into the sky involves 5 very precise steps. First, obviously, a massive rocket launch just to overpower gravity. Then the unused stages of the rocket separate once it hits space. But step 3, that is the real trick. The rocket has to push the satellite perfectly horizontally, achieving that insane orbital velocity so it can continually miss the Earth as it falls. Finally, we make fine orbit insertions, deploy the solar panels, and it's good to go. Okay, section 3, the geostationary magic trick, literally hovering in space. Now listen, not all space is created equal. There is actually a highly specific Goldilocks zone up there where satellites seem to perform a literal magic trick. If you place a satellite at exactly 35,786 kilometers above Earth's equator, it's far enough away that gravity's pull creates the absolute perfect conditions for something spectacular to happen. What's so spectacular? It's the time it takes to orbit. At that very specific altitude of 35,786 kilometers, the orbital period takes exactly 24 hours. Well, to be incredibly precise, roughly 23 hours, 56 minutes, and 4 seconds, which is one sidereal day. But the point is, this perfectly matches Earth's rotation. Because the satellite and the Earth are rotating together, west to east at the same speed, to anyone standing down here on the ground, the satellite appears completely motionless. It is totally fixed over one single point in the sky. Magic. That brings us to section 4, different orbits, different jobs, a custom fit for space. So space definitely isn't a one-size-fits-all environment. We actually rely on very different orbits to solve very different problems down here on Earth. As you can see, geostationary orbits are absolutely amazing for continuous communication because they can stare at 1/3 of the Earth nonstop. But they can't effectively see the poles. So for that job, we use polar orbits, which are much, much lower, around 200 to 1,000 kilometers up. These don't look stationary at all. Instead, they zip aggressively around the poles while the Earth just slowly rotates beneath them, allowing them to scan, map, and photograph the entire globe over the course of a few days. All right, class, Section 5, the cheat codes of physics. Hacking gravity. Okay, let's take a quick look at the math behind the magic. And please don't panic. These aren't scary textbook equations. I want you to think of them as the literal cheat codes that scientists use to hack gravity. Newton's law of universal gravitation tells us exactly how strong that invisible string of gravity really is. The force equals the gravitational constant times the mass of the Earth times the mass of the satellite divided by the distance squared. All this equation is really saying is that larger masses create way stronger gravity. But as you get further away from Earth, that pull gets rapidly weaker. In fact, just doubling your distance from Earth actually cuts gravity's pull down to 1/4. And because gravity gets so much weaker the further out you go, you logically don't need to travel as fast to fight it off. This orbital velocity formula proves exactly that. A higher orbit requires a lower speed. Low Earth orbit satellites, the ones that are super close to us, have to absolutely zip around at a blistering 7.8 kilometers per second just to avoid crashing. But those geostationary satellites we talked about, way out there at 35,786 kilometers, they can take a much more leisurely stroll at just 3.07 kilometers per second. It's brilliant. Section 6. Satellites in everyday life. The invisible helpers. So why does all this orbital physics actually matter to you and me when we're firmly planted on the ground? Well, because of the totally unique properties of geostationary orbits, they are the true unsung heroes of our modern daily routines. Because they hover in one spot, they are what brings you live international sports without any interruption. They allow meteorologists to capture images of almost an entire hemisphere every few minutes, giving us those absolute life-saving early warnings for cyclones and hurricanes. And all of this crucial data just beams directly down to a fixed satellite dish on your roof that literally never has to move. Meanwhile, other highly specialized orbits are up there picking up the rest of the slack. Medium Earth orbits, or MEOs, are perfect for running the GPS systems operating in your car right this second. And those fast-moving polar orbits, they're actively monitoring melting glaciers for climate change. They're tracking devastating wildfires for disaster management. And they're even helping farmers optimize their irrigation through precision agriculture by literally identifying water shortages from space. So if you take anything away from today's explainer, make it this. Understanding that delicate, invisible balance between a satellite's forward inertia and Earth's inward gravity is what has allowed us to engineer an incredibly connected world. The simple fact that a dish on your house can just point at a seemingly empty patch of sky and stream the internet is entirely because Arthur C. Clarke's crazy 1945 sci-fi idea was backed by Newton's flawless math. It truly makes you wonder, doesn't it? The next time you gaze up at the stars tonight, I want you to ask yourself a question. How many of those tiny, steady points of light aren't distant suns at all, but rather testaments to human ingenuity? How many of them are multi-million-dollar machines perpetually and gracefully falling around the Earth without ever hitting the ground? Thank you so much for joining me for this explainer today. Keep looking up and keep asking questions.